Class Electric Current Part 4. In the class, we are going to learn what are laws of resistance. Already we learned Ohm's law and we defined resistance. So in this class, we are going to learn the laws of resistance. What are the laws of resistance in detail? Children, you observe this circuit. Electrons are flowing in a closed circuit. The flow of electrons is nothing but electric current that is recorded with the help of the ammeter. The deflection in the ammeter, you observe this one. The deflection in the ammeter shows current is flowing in the circuit. Now, here I have taken aluminum as the conductor here. Observe this one. Okay, aluminum as the conductor. So, I recorded the current flowing through the aluminum conductor with the help of the ammeter, and I recorded in this table, let it be I1. After that, I replaced this aluminum conductor with copper. Here in the second instance, I have taken copper as the conductor. Now current is flowing. I observed the ammeter reading. I recorded my observation and I2. Okay, clearly I observed that I2 is greater than I1. Next, I replaced this conductor copper with silver. So now silver serves as the resistance. It offers certain amount of resistance. Now I observed the reading of the ammeter. I clearly observed that in the third instant when I used silver as the conductor here at this joint, see, I observed more current is flowing in the circuit. So I recorded with the help of the ammeter. So with all these three observations, it is clearly understand that in the beginning I have taken aluminum as the conductor, next I have taken copper as the conductor, I have taken silver as the conductor. In all these three instances, see, I observed that the current flowing in silver is more than copper, is more than aluminum. So I can conclude that silver is the good conductor because it offers less resistance. But we are not using silver as the conducting wires nowadays because silver is the costly metal when compared to aluminum and copper. So copper is the best conductor because it opposes less resistance to the flow of the electrons. So we can use copper as the conductor because copper is allowing less resistance to the flow of the electron. So with this experiment, we can conclude that the resistance offered by a conductor depends on the nature of the material through which it is made. So aluminum, copper and silver. You can take different metals also as the resistances here at this junction. So the resistance offered by a conductor depends on the nature of the conductor. With this experiment, we can conclude that the resistance depends on the nature of the material through which it is made. Children, you observe this one. I am not changing the potential difference in the circuit. Potential difference is kept constant. Now, what I did in the beginning, I have taken a conductor of length L. So, with the help of the ammeter, I recorded my observation. The current flowing in the circuit is I1. After that, I doubled the length of the resistance. Then I recorded my observation. The current flowing in the circuit is I2. After that, I tripled the length of the conductor. Okay, so I am not changing the area of cross section. Simply I am changing the length of the conductor. I recorded my observation it as I3. So in all these three observations, I observed that as the increases length increases, the resistance offered by the conductor also increases. The resistance offered by the conductor is also increasing. So we can conclude that when the length is increasing, the current flowing in the circuit is decreasing. From this observation, we can conclude that the current flowing in the circuit I is inversely proportional to length of the conductor. As the length increases, current decreases. As the length decreases, current increases. Are you clear about that one? So this is the simple experiment which shows the length. As the length of the conductor increases, current flowing through it is decreasing. Okay. Now children, you observe this another circuit. Here I am not changing the length of the conductor. Simply, if you observe this, I increased the area of cross section of the conductor. Area of cross section is increased. So, when the area of the cross section of the conductor is increased, so the more and more current is passing through the circuit. So, more and more electrons are passing as the area of the conductor is increased. Are you clear about that one? Just like when there is a narrow converter, it is very difficult to the vehicles to pass through it. If the converter is wide, more and more vehicles can pass through easily. In the same manner, here more the area of cross section of the conductor, more and more free electrons are flowing through the conductor. So, as the area of conductor increases, the current flowing through it increases. So, the current flowing in a conductor is directly proportional to the area of cross section of the conductor. It means that larger the area, larger the amount of current flowing through the conductor. Summarize all the experimental facts which we did. See this one. In our previous experiments, we experimentally found that the current flowing through a conductor is directly proportional to area of cross section. More the area, more the current. More the area, more the current. The second one is the current flowing through a conductor is universally proportional to its length. If the length of the conductor is more, less the current flowing through it. So when we summarize these two, I is proportional to A by L. In our previous class, we studied that current through a conductor decreases if resistance of the conductor increases. So current flowing through a conductor is inversely proportional to R. I is proportional to 1 by R. From the above equations, 1 by R is proportional to A by L. 1 by R is proportional to A by L, or A by L is proportional to 1 by R. At the same time, to remove this proportionality, I have taken a constant known as the proportionality constant, which is known as specific resistance or resistivity. So R is equal to rho into L by A. So this rho is known as what we call it resistivity. This rho is known as resistivity or specific resistance. How can we define it? It is the resistance of a specimen resistor of unit length and unit area of cross section. The units are ohm meter. How you got ohm meter here? Look carefully. See, length is measured in, what are the units? Length is measured in meters. Area of cross section is measured in meter into meter, that is meter square. So when you substitute this, resistance measured in ohms and area of cross section is measured in meter square divided by meter. Meter and meter gets cancelled. What are the units? Ohm meter. So this is the cube whose length is the length of the cube is equal to how much? 1 meter, and the area of cross section is 1 square meter. So just I have taken to make it clear, this is an example. What do you mean by 1 square meter area and 1 meter length cube? So this is the specific resistance or resistivity, is nothing but it is the specimen resistor of unit length and unit area of cross section. So this is the resistance offered by this cube whose length is 1 meter and whose area of cross section is 1 square meter. This is known as specific resistance. Children, I think you are clear about this laws of resistance. So what are the laws of resistance? The first law says that the resistance offered by a conductor is directly proportional to its length. At the same time, the resistance offered by a conductor is universally proportional to area of cross section. Its area of cross section. The important one of the another important thing you have to remember is that resistance always depends on the nature of the material. Okay, different materials will have different resistivities. Okay, thank you children. I think you are I make the chapter very clear with these lab activities. Thank you children. If you like my video, please subscribe and do watch my videos. Don't forget to watch my videos. Thank you children.